Hi, in this video we are going to talk about the so-called traveling salesman problem. So let's get started. So what is the main problem? Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and returns to the original city? So this is the main question behind the traveling salesman problem. It is a typical NP-hard problem in combinatorial optimization. So we have n cities, and we have n factorial permutations, so brute force methods cannot be used. It is possible that the worst case running time for any algorithm for the traveling salesman problem increases exponentially with the number of cities. And it has something to do with the Hamiltonian path. So what is a Hamiltonian path? It is a path in an undirected or directed graph that visits each vertex exactly once. Another important path in a graph is the so-called Euler path. In an Euler path, we visit each edge exactly once. So in the Euler path, we visit each edge exactly once, and in the Hamiltonian path, we visit each vertex exactly once. A Hamiltonian cycle is of course a Hamiltonian path that is a cycle, and if there is a Hamiltonian cycle in a graph, then the solution of the traveling salesman problem is the Hamiltonian cycle itself. So let me tell a few words about the algorithm itself. The most direct solution would be to try all permutations. This is the so-called brute force search. But as the running time it's based on the permutation of the number of cities, so it's very impractical even for 20 cities. And dynamic programming approach, the so-called Halb-Karp algorithm, solves the problem, but it is not too fast. So the principle is we just want to get an approximate solution. It doesn't need to be the best. So it can be done with Monte Carlo based simulations. And it's very important nowadays in the 21st century that if we have NP hard problems, which would be very hard to solve algorithmically, we just usually generate random numbers. This is the principle of Monte Carlo simulations, and we just want to get an approximate solution. And we know that it's not the best, but it is quite good solution for a problem. And the advantage of these kind of simulations that it can be done not so fast, but it's much faster than the brute force search, for example. So methods for solving the traveling salesman problem. The most basic solution would be to choose a random tour. It's not so efficient as you may think. The greedy search is the next one. We always choose the next nearest city. It is a bit it is a better solution than a random tour, but we can do definitely better. So there's a 2-up solution: generate random tour, take a route that crosses over itself and reorder it so that it doesn't. If the tour overall distance cannot be enhanced with swap of edges, then this is the end of our algorithm and we terminate. But there are several simulations with which we can help our problem. The so-called simulated annealing, it's quite good. It can avoid local minimums. It's like Metropolis Hastings algorithm. In the Metropolis Hastings algorithm, we allow non-optimal sub-solutions too with given probability. This probability is a constant, and this principle is very important because with the help of this we can avoid local minimums. The first simulation where physicists used the Metropolis Hastings algorithm was to solve the so-called Ising model, and with the help of Ising model a lot of questions can be answered as far as magnetism is concerned, and it is a very good model, and it can be solved with the help of Monte Carlo simulations, and this is the base of the Metropolis Hastings algorithm. So the simulated annealing, the probability is changing too. We have a parameter called a temperature, And as the temperature decreases, the probability decreases too. So we reject bad solutions as defaults. We are going to see it during the implementation, so it will be clear. So the simulated annealing is that we accepting worst solutions is a fundamental property of meta-heuristics because it allows for a more extensive search for the optimal solution. And as I said earlier, that these kind of simulations can avoid local minimum. For example, the so-called hill climbing algorithm, we keep moving towards the gradient. It can be defined with the help of partial derivatives, and it is not so optimal because we can reach a conclusion where we stuck inside the local minimum instead of the global minimum. And this is why simulated annealing is very, very efficient, because we can avoid the local minimum and we can definitely find a global minimum what we are after. So we initially set the temperature to high and then allow it to slowly cool as the algorithm runs. While this temperature variable is high, the algorithm will be allowed with more frequency to accept solutions that are worse than our current solution. We will see that sometimes we start with a random tour, where a tour means the permutations of the cities. And after running the algorithm, we end up a solution that's worse than our initial one. So we usually run this kind of algorithm, the simulated annealing, several times, and we calculate the average. And this is quite a good solution, we are going to see. So this gives the algorithm the ability to jump out of any local optimums, as I said earlier. We keep select edges at random, and this is why the Monte Carlo based algorithm, and keep swapping them with a given probability. And as I said earlier, as the t parameter, the temperature, keeps lower and lower, we keep rejecting wrong solutions. So it's going to be clear during implementation. So in the next video, we are going to start our simulated annealing algorithm. Thanks for watching.